Okay, in this video we're going to finish off our notes for section 5.5 and then the next couple of videos are a couple of examples. Alright, so the next topic in this section is this thing called the method of variation of parameters. So I'm just going to talk about why we're doing this, what it's about, and then we'll get into some of the details. And then the next video will actually go through this example that's here on the screen. Alright, so first of all, there's a theorem here, and we want to pay attention to what kind of differential equation this theorem is about. So there are several important things here. One, this is a second order, linear, ordinary differential equation. It is written in the form where the lead coefficient is 1. So if you started with a differential equation that was not in that form, actually the last example in our class notes is like that, the first thing you would want to do is get it in that form, right? So lead coefficient of 1, and because there is not the zero function on the right hand side of the differential equation, this is a non-homogeneous differential equation. Alright, so that's the kind of differential equation we are looking at. Notice that our example over there, for example 8, is that kind of, except it has t for the independent variable instead of x. So then what you call the variables isn't important, it's just important that you have it in this kind of form. The coefficient functions for y prime and y have to be continuous on some interval. Okay, so we've been checking for continuity of coefficient functions for a lot this semester, so you should be used to that. On our example, our coefficient functions are 0 for the y prime term and 9. So as functions, those constant functions are continuous everywhere. The f of x function on the right hand side is integrable, right? So that means that a definite integral exists on some interval. So I can integrate the cosecant function from a to b for some interval a to b and get a finite answer. Okay, so you can do that. You learned how to do that in Calculus 1. Alright, and then it says here if y1 and y2 are linearly independent solutions of the associated homogeneous equation. Alright, so we again are going to be looking at finding a solution for the yh part. And the two linearly independent solutions that make up that yh part, which is going to come from solving that associated homogeneous equation, would be your y1 and y2. Right, so we know how to do that for a lot of differential equations, not all of them. So example 8 that's here, you know how to do that for example 8 because you have constant coefficient functions. Example 9, that is at the bottom of your page of notes, or let me scroll down here, we don't exactly know how to handle that one yet. So you'll want to watch that next video to think a little bit about how we're going to handle that with those variable coefficients in that one. Okay, so then it says that yp equals u1. Okay, so it hasn't talked about what u is yet. Yp equals u1 y1 plus u2 y2. Those are all functions of x. Alright, so the y1 and y2 come from our yh, the two linearly independent solutions of the homogeneous equation. And we got this u1 and u2, so let's read the next part that tells us about that. It says that that will be a particular solution to the non-homogeneous differential equation 2. That was the original equation we started with, where u1 and u2 satisfy this system of equations. Okay, so this system of equations here is what we're going to need to work with to find u1 and u2. And then we'll be able to write the yp, what it says up above. Yp is going to be our u1 function times y1 plus u2 times y2. And then we also know that what it says in some of the notes below are some kind of follow-up comments. And so this first one says, this tells you how to find your yp. And then you will use that to create the general solution like we did before. Remember that the y is yh plus yp. Alright, so kind of the two main parts, finding the yh, finding the yp. This is just a different method for finding the YP. So the other question would be, why do I need to learn another method? Because we already did undetermined coefficients. And so there's some other comments here that talks a little bit about that. I guess it's in bold, so I'm going to skip down there and talk about that. If the method of undetermined coefficients works, that is usually a lot easier. So use it when it works. But remember that in order for that method to work, I needed to think about that f of x function, and all of its derivatives had to form a finite list. And we don't have that for the example that we are looking at here. So I'm going to do the example in the next video, but I want to just talk a little bit about why we can't use undetermined coefficients here. So this f of t function, if I think about that function, and then the derivative of the cosecant function is negative cosecant cotangent, and I get an extra 3 from chain rule. So negative 3 cosecant 3t times cotangent 3t. So that's a product of two functions. So I can't think about that as two separate functions. That's a whole function. And then if I think about the derivative of that, well, when I find the derivative of that, I'm going to have to use product rule. And so it shouldn't take you actually writing down that derivative to think through things like that the derivative of cotangent is negative cosecant squared. And so you're going to end up with a cosecant cubed 3t term in there, to realize that your derivatives are just going to get more and more complicated, and this list is going to go on forever. So undetermined coefficients would not work for this problem because of this cosecant function. All right, so we're going to have to use something else, so that's one reason we're learning something else. Okay, so a couple of other comments. I'm not going to read through all of these right now, but you should read through them and just notice. For example, number 3 talks about extending it to higher order ones. There aren't any in our homework, but it can be extended. There are some other things to talk a little bit about here. There are a couple of difficulties in using this method to find YP. So first of all, you have to be able to find your two linearly independent solutions. That's not necessarily hard, but you might have to do that. And then another difficulty is in finding U1 and U2. Finding this U1 and U2 that you're going to use, you're going to find from this system that I kind of marked up here. So notice that that system of equations doesn't actually have U1 and U2 in it. It has U1 prime and U2 prime in it. And I need to find U1 and U2, so I'm going to have to undo some differentiation in order to make that happen. And so I'm going to have to evaluate some integrals to do that. And so sometimes that's easy enough, not too hard. Example 8 that we're going to look at here is pretty straightforward. So is example 9, but you know that you could have some integrals that are pretty crazy to try to evaluate, or maybe are impossible to evaluate in closed form. So that's one issue with using this method. There's a little sketch of the proof for this theorem in your textbook. It's fairly long and involved, but it kind of explains why this technique works. I don't think it's necessarily obvious from looking at the system of equations why this should work for giving you a YP solution. So it's kind of a long and involved proof, but there's a proof. That is kind of the point there. All right, and then the other thing I want to mention is this last point here. Sometimes I see students try to use another version of this theorem. It is in the textbook. If you look online for some other help, other videos, or whatever other sources of help you sometimes go to, you might notice them using some different method for the theorem. That theorem is given on page 324 of your textbook. I don't mind if you use it, but even though they give that other form of this theorem, the example in the textbook actually doesn't use the alternate form of the theorem. I a lot of times see some students who are sort of looking for a shortcut try to use that theorem, but the difficulty is that there's a lot of notation in there, and a lot of times I see students have trouble actually using that theorem correctly. So just kind of a warning, if you look at a source and they're using really a different technique than the one I'm using, in that next video. That's okay, probably, but you need to be sure that you're clear about the details. So whichever way works for you is fine. Alright, so I'm going to just kind of sketch right here what we're going to do for this example 8, and then I want you to watch the next video where I actually go through it. Alright, so we're going to start by finding the YH, and we know how to do that already. I'm not going to write it down in this video because it's in the next video, but we're going to solve the associated homogeneous differential equation. And when we do that, we're going to get a fundamental set of two solutions that will form the general solution for the YH. So we'll have C1 times one function. Maybe you can kind of see your way to the finish line here and see what that Y1 is. And then plus C2 times the second function. So we're going to use those, that Y1 and Y2 from that YH, we're going to use in that system of equations to find the YP. Alright, so to find the YP will be U1 times our Y1 from that prior step plus U2 times the Y2 from that prior step. But the issue is that the U1 and U2 are not just coefficients, those are actual functions. So I have to find the U1 and U2. I'm going to do that by setting up that system of equations. You will want to put that on your formula sheet for exams or in the semesters when we don't have formula sheets. Students just learn this little system of equations. So maybe after you do a problem or two, it's not that hard to remember. So let's see, we've got the Y1, Y2, and Y1 prime, Y2 prime, and then the f of t function. That is that function from the right-hand side of your differential equation. So for this particular problem here, that f of t function is going to be cosecant of 3t. Alright, so if you want, you might try solving that and then check in that next video to see if you did it correctly, or just go ahead and watch the video where we'll go through this example.